think we're good. It's recording, yes?
Yeah, it is.
Okay, thank you. So I know that stoichiometry is something that not only have you done, but you were really good at. I think if you were excellent in Chem 1, then you know stoichiometry really well. Because not only do we study a chapter on stoichiometry, but every chapter almost after that, we can build problems with stoichiometry into it. So you just can't help but be good at it. In fact, stoichiometry is the most used concept in this class. And you cannot go through this class without being really good at it. I have two problems for you today. One's an easy Mickey Mouse problem, and then the other one is a really, really hard problem. And that's it. We'll call it a day. No.
What class do you have before this?
Did you see what I erased?
Yeah. That's the problem.
Probably not,
Okay.
but maybe.
C4H10 maybe, right?
Don't say it out loud. Jess,
Any plans for the weekend?
Jess, I'll talk to you later about that.
Sorry. We're writing notes down.
That's right.
Trying to kill some.
I have cross country this afternoon and cross country tomorrow. That's the excitement.
Maybe Samir and your son will be at the same meeting.
They're not. No, they're in different places. Next week though, they'll be in the same. I get to cheer for Samir next week, Wednesday.
Tackle him.
Yeah.
Maybe.
It's a form of motivation, actually.
It really is.
Yeah.
He just wants to run away.
So you know that with stoichiometry, you always have to go through the unit moles. You cannot do stoichiometry without having moles, or without going through. The coefficients in the balance equation are really the anchor for the problem. You've got to get to moles, use the coefficient ratio, get to the moles of the new thing, and then convert to whatever unit you need. So I have a simple, this is just, I don't write this as a challenge kind of thing. I just write it as a, okay, can you do a simple stoichiometry problem? And before you start this thing, what I would like to suggest, and this is not just for this problem, but for all stoichiometry problems that you do, when you're given the equation and given the problem, find what your given quantity is. We're given 30 grams of iron. That's a product, but we know that amount. So I'd find iron in the chemical equation and write that amount underneath it. The question is, what mass of iron 3 oxide is required? So this is what I'm trying to find. So I'm going to call that one X and write to myself what unit I want to get to. That helps me to organize the information in the problem, and then I'm off and running with it.
For quizzes and tests, we can only use the scientific calculator.
Yes, for quiz and test, only a non-graphing scientific calculator, non-programming. And get a lab notebook this weekend too, or by next week. Yes.
Can it be the same one as notes on it?
I would suggest not, because I may have them for a couple days.
Are we doing the problem?
Yeah, I'm giving you time just to work through the problem. Yeah.
swear I did not. I swear. Remember I came back and showed you my grade last year?
Yeah, maybe I do.
That was when you gave me the lecture about how I can't keep getting by without taking notes. Do you remember that?
I do. I wouldn't call it a lecture now.
Or
Call it a,
advice.
yeah, a well-structured and intentioned suggestion.
Yeah, lecture has negative connotation.
That's right, that's
He
right.
did not do it in a mean way or in a way to make fun of me or in a way that I thought was useless. It was good advice.
Okay.
I just never.
And you just- I knew.
I don't know what else to say.
The key to stoichiometry is that moles are the anchor. If you're not in moles already, you have to get to moles. And then you can use the 1 to 2 ratio. All right, so I'm assuming that you're almost done or done with the problem. I'm going to go ahead and set up, because I have something else I'm up to with this one too. I do want to encourage you, if your Chem 1 teacher showed you the railroad track method for, with just the horizontal and the vertical lines through there for doing conversions, keep using that, because I'm sure you're very comfortable with that. I'll never give you a hard time about that. I don't know if this looks strange to you. It's the same operations, though. Now, my question is this. Assuming that you have it set up like this, can we do this? You know how in the multiple choice we can't use a calculator. Can we do this without a calculator?
Yeah, no, yes, yes.
30 and 55 and 2 and 159. I think we can. And you'll have a lot of stoichiometry and problems like this to try to do without a calculator. So let's see what we would do. Try to simplify as much as you can. And if you have to estimate wisely. Of an
So why are people not taking the calculator?
Because the AP exam doesn't allow you to use one in the multiple choice, so we just want to be consistent with that. Yeah?
Not everybody.
Right. On the multiple choice, you can't use any at all. Yep, Jess?
Quiz is fine.
Quizzes you can. Yep, for all quizzes you can use a calculator. And the free response, other second half, you can use one too. Just that multiple choice you can.
The answer's like far apart.
Hopefully. They should be, expect that. Yeah. Yeah. Because like on this, you're going to see, this is a great point to make because of what Regan just asked. Are the answers far enough apart that it should be obvious? Check this out. So trying to estimate and come up with an answer without using a calculator, I don't see anything that's real obvious. I like the 2 down here because 2 normally you can find something that you can cancel. So let's do this. Let's take the 2 and make it a 1 and factor 2 out of the third to make it 15. Now I got 15 there, 55.8, and 159.6. That doesn't go very nicely into that, does it? Not really. I guess a little bit it does. You could say that is about 1/3 of that, approximately, yes? And then, so if that's a 1 and that's a 3, multiply by 15 is about 45.
Wait, say that all again, I'm so sorry.
What?
You say all of that again.
Yes, yeah, I will. There's two different ways that we can try to continue estimating. This is about 1/3 of that, right? That's about halfway through 50. 3 times 50 is 150, so that's pretty close. So that is a 1, that's a 3. And then you can just multiply the 15 times the 3, and you'd have about 45. Do we get an answer with the calculator? What is it? 42.9. So estimating that to be 45, that's pretty good. Close enough? All right. You could also say, okay, that's 15. That's pretty close to 60. So just reduce that 1 and 4, and then you have a close to 160 divided by 4 would be about 40. So I do want you to know that on tests, when you can't use a calculator, we will use numbers that will get you pretty close to the correct answer. And so you just want to look for which of the answer choices is close. It may not be exact. Don't freak out if it's not. It'll be close. And the numbers will be, this is not probably a question with the numbers like that I would ask on a test. You know, I might say that you have 110 grams of Fe. So then when you divide 110 by that, you get something very close to 2. Yes, and then you go from there. In fact, that would make the problem really easy because the 2 that you would cancel there would cancel with the 2 there. You'd be left with that number. So, yeah, the numbers will be nicer. These are just made up straight out of the book, I think. But we're going to practice. I'm going to give you a lot of coaching on doing these no calculator problems. Anybody have any questions about that process of stoichiometry? We first take the grams. We got to get into moles first. There's my mole conversion. Then we use the coefficient ratio. It's a 1-to-2 ratio. Always put the unknown number of moles on top in that step. So there's my unknown, 1/2. And then finally get back to grams of my new substance and using that mole mass. The next thing that I have for you, I told you that we have a hard question coming up now. This is it. The hard question is going to involve another concept. Molecular formula. Now, you read in the reading assignment about empirical formula. The empirical formula, though, is not always the actual formula for what's in the molecule. The empirical formula, as we know, is the lowest ratio of elements in a compound. But if you want to take a moment and just write this down, I'll show you what I mean, how the molecular formula is different from the empirical formula. The compound ethane. What's its formula?
C2H5, H6.
C2H6. That's ethane.